Um, so last week we were talking about the formation of the solar system, formation of our planet. Many of you watched a video last Friday that kind of hit most of what we're talking about already, especially today. The video really hit a lot of today's stuff. On Monday, you guys did, or we did together, talk a little bit about Earth, early history, and the layering of Earth and things like that. Wednesday, we did the radioactive dating game, and I did hope that you kind of took that game a little serious as far as like learning what scientists have to do, what works, what doesn't work, how scientists have to be creative about this or that. In the end, things do work, but there are some limits, there are some pros and cons to that kind of stuff. One thing that some kids and people say in general that, if scientific equipment or things like that have a limit and they don't work all the time, then it must be wrong. Like, that doesn't make a lot of sense. Like, just because you can't use it every single time doesn't mean I can't do it for what it's used for. There's limits to everything. Limit to cell phone, limit to computer. I can't hammer in a nail with my cell phone. Does that mean my cell phone is dumb and pointless? No, of course not. Okay, so same thing with science equipment. They are going to have limits. That's the whole point, is you guys go to college and make them better. Invent a better way of doing what we're doing today so we get better data. Okay, and again, if you invent something really cool, you can make quite a bit of money doing that. Okay, so today we are going to talk about the atmosphere, because Earth is a special planet. It's actually a really special planet, especially comparing it to our own solar system. We are very unique. For us to say that we are the most unique planet in the universe, well, that's a little selfish, that's a little arrogant to say. I doubt we are that unique, but we are definitely, certainly pretty unique. And the fact that we have a viable world for living things to live on. Okay. And so today we're going to talk a little about that history, because it is unique, that history and how it happened, and all the things that did have to kind of go right in order for Earth to be where we are today. Okay. So you have the note, you have the worksheet, if you guys want to follow along. Okay. Welcome, Aid. Okay. And let me share my screen as well so that everybody can see it. So the very first thing I want to talk about today, and again, you kids at home, if you have any questions, just type them up. If you kids here have any questions, make sure you ask. You have the note, so I'm not going to go read the note word for word here. I'm just going to talk about other stuff and enhance the notes a little bit. There is a lot of technical stuff that happens in Earth's history. We don't need to know the nitty-gritty stuff. You just need to know those 7 or 8 questions I'm asking you today. We just need to know the basics, okay? Especially for freshman high school science. Okay? It does get very complicated, as you can imagine. Okay? So one of the very first things I want to talk about real quick is, on Monday, we talked about the Earth having layers. And one of the questions that some kids brought up is, how do we know that the Earth has layers? Have we ever gone in there? Have we ever looked at the inside of Earth? Question is no. The answer to that is no. We have not actually gone to the middle of the Earth to see what's inside of it. Okay? And we probably never will. Okay, that's not really a very viable thing to do. But there is data that we can collect today and kind of prove what is on the inside of the Earth, as far as the Earth having layers, the core, the outer core, the mantle, all that. Okay? One of the deepest holes that we have ever drilled is called the Kola Super Deep Borehole, and that's about 12.2 kilometers deep. Even that hole, the deepest hole we've ever dug, still doesn't come close to actually breaking through the crust. The average thickness of the crust is 15 to 20 kilometers, but the continental crust where we are is really thick. The thinnest crust is at the bottom of the ocean, where that C4 spreading is happening. That's where the thinnest crust is. And as you can imagine, it's really difficult to drill a hole in the middle of the ocean like that. So the deepest holes that we've drilled are not really that deep. And no, we have not even gotten close to looking inside the Earth. Even if we did, what will we send down there? It would just melt. It's magma. It's, whatever probe or, device we send down there is not going to last very long. Okay. So how do we know what the inside of the Earth looks like? Any suggestions without looking at the next slide? What do you guys think? How would you look inside something that you couldn't look inside? What would you do? Okay. Yeah. Okay. Okay. Can you guys hear anything? Can you guys even hear me? That's really annoying. All right. Okay. Thank you. Yeah. So we can actually collect data on the interior thing without getting into them. And one really common thing you guys already know would be things like an X-ray machine or a CAT scan or MRI or ultrasound. All of that is putting energy through the object and having instruments to record what happens to the energy when I send it through the body. Okay? Well, X-rays are quite energetic. They can cause damage to you, so you want to be careful with X-rays. But ultrasound is another one. Oh, this is an ultrasound picture. You guys can probably imagine what that picture is there. A little baby inside of a woman there. And you're putting sound energy into the body, and you have instruments that catch the reflection or the bouncing back of the sound energy as it bounces off things. So you can put energy into objects and then record what happened to that energy. And so if we really wanted to, I could put a seismograph or a seismometer in China or Japan. I could stomp my feet really loud, send my energy to China and Japan, and they could pick it up on their seismograph. I could do that if I wanted to. I'm not going to be able to make enough energy to send it all the way to China and Japan, but there are earthquakes. We do have earthquakes. Earthquakes have enough energy that they send their energy, their wave energy, across the entire planet. Okay? Even small ones. The energy can be picked up in other countries, in other places. Obviously, it's going to do less and less damage as you get further away, but if China had an earthquake, we could pick it up here in America and be like, oh, something happened over there. Okay? If we had an earthquake, they could pick it up. Because that energy does go through the earth, the entire earth. And when that energy goes through the earth, it changes direction when it hits things, when it goes through things, when it goes through layers. If you guys have ever tried this with your brother, sister, your cousin, something, you ever have two cups, and you put a piece of string between two cups. You talk into the cup, the sound can go through the string, you hear it on the other side of the cup. You can do it pretty far away. Okay? Sound or energy loves to travel through things that are more dense. The denser the object is, sound travels a lot further. Okay, if I wanted to send a sound wave to somebody, I would use a metal pipe, hit it with a hammer, they would hear it miles away. Okay? You can even talk through water a lot better. Whales can talk to each other miles and miles away because sound travels better in water than it does in air. Okay? Us humans, we can talk kind of far, but not that far because we're talking in air. Right? Waves do the same thing. When they travel through different densities, they behave differently. And so, if I put seismometers all over the place, and we have an earthquake, we can see what happened to the wave. We can see what happened to the energy. And as the energy passes through the core, the outer core, the mantle, it changes direction. And using that information, we can put a picture of what the inside of the Earth looks like. Not only that, we have a magnetic field. We know that there must be some iron in there that's producing a magnetic field around Earth. Okay? And so with the magnetic field, with the energy from the waves, from earthquakes, we can map out the interior of the Earth pretty well. We're pretty sure that's what it looks like. Okay? And again, it's just not some person's idea. His data is scientists backing up each other, saying, yeah, I agree with your data, I support that. So, kind of moving a little bit along here. Let's talk a little bit about the actual transition for our atmosphere and how Earth got here today. And again, we're focusing on the fact that Earth is a really relatively unique planet, and all the processes are really important for this. And we're going to compare it to Venus and Mars later toward the end of class. So first thing first, we need to remember that early Earth did not have water. Okay, and I think that's one of the very first questions on there. Did early Earth have water? No, it didn't. It was too hot. It was just vaporized. Again, you're talking about a molten magma planet at this point. Okay? It did not have water. It was too hot. As it was starting to form, it ran into the moon. That made it hot again. Okay? It didn't have water. Water came much later. Well, not much later, but it came later. Okay? Earth had to cool down first. Okay? Once Earth started cooling down, where did the water come from? If it didn't have water, where did it come from when it started cooling down? What else has water in our solar system? Even today. Not very many planets have water. They kind of do, but not very many. Not the asteroids. Not the meteors. So once the Earth started cooling down, the water started coming from comets. And again, remember, we're talking early solar system here. There's a lot of stuff out there. There's a lot of dust. There's a lot of junk out there. Gravity bringing all that stuff together, including all the comets. Gravity bringing all that back together too. So as Earth started cooling down, and you're talking hundreds of millions of years with no water, the comets start bringing the water to Earth. And the water can stay here because we're in that Goldilocks zone. We're not too hot, we're not too cold. The liquid water can stay on the surface of Earth. Okay? Then again, water came later after the land settled and goes from there. So you're probably thinking, Mr. Cannon, there must be a lot of comets. Yeah, it was. You're talking hundreds of millions of years of getting hit by things. Yeah, that's a lot of water. That's a lot of comets. That's a lot of ice. Fortunately for us, the solar system is pretty clean now. Gravity brought all the stuff together. We're not getting hit by comets like we were 4 billion years ago. Okay? The 4 billion years ago, yeah, we were gathering a lot of stuff, a lot of comets, a lot of asteroids, a lot of meteors. We're all coming together because that nebula was gravity pulling it on in. So liquid water came later. Okay, so that is kind of a first important fact. And liquid water is going to be important for the next part too, our atmosphere. So early Earth, again, this picture here represents Earth without water. Remember, Earth is a rock planet. It is not a water planet. People, I'm not kidding, people still think that. People still think that Earth is mostly water. No, it's covered by a lot of water. But it's not mostly water. It is a rock planet, okay? It is mostly rock, melted metal, melted metal. That's what Earth is mostly, okay? Water is on the surface though, covering most of the surface. And back in the early days of Earth, it was covering the entire planet. So we didn't have continents back then. We'll talk more about that in a second. But on Earth, water is about 0.1% of Earth is water. That's not very much, okay? Of that water, most of it is salt water, not things that we can drink. So you go down this little bubble right here. I don't know if you guys can see it very well. Go that little bubble. That is fresh water. Okay, so of all water, a tiny bit is fresh. However, most of that fresh water is locked up in ice in North and South Pole. I don't know if you can see it. That little itty bitty dot right there. That little itty bitty dot is the drinkable water that we have here in our world. So all 8 billion people on Earth are fighting for that little bit of water that they can drink and use as a resource. Our fresh drinking water is a very small amount of the water that's here on Earth. And we're not getting more water. Okay? There are not a bunch of comets that are hitting us today. Right? That's good. But we do need to take care of this resource. And again, this whole unit, the whole purpose of what we're talking about is where do our resources come from? And how are we using them? Well, water is a very important resource. You need it to live. It takes about 3 days with no water, you're done. Okay? You need water. Everybody needs water. Okay? We're not getting more of it. We need to take care of it. We need to be mindful of it. If we don't, we start running out of water, people are going to start fighting for it. People are going to go to war for this resource. That's right, for water. It's already happening. A lot of places are already doing that. You know, they're fighting for lakes, they're fighting for the rivers. Okay? And so, again, these resources, we need to understand what's happening to them. Okay? Because they're not unlimited. Now I will say this. Can we turn the salt water into drinking water? Yes, we can. It's very difficult. It's very expensive. So who's going to be able to do that? The rich people, right? The third world developing countries are probably not going to have that resource, and they're going to get mad and they're going to fight, right? I would too. So again, we need to think about ways to equally use our resources amongst all 7, 8 billion of us in the world. If you can invent a way, literally that's your job, you're my engineers. If you can invent a way to take salt water, make it into drinking water, fast, cheap, and effectively, you'd be a billionaire overnight. Like literally. Okay, so figure out a way to do that. Figure out a way to take the salt out of water, fast, easy, cheap. And we can do it, it's just expensive. All right, so let's talk a little about our atmosphere. So we talked about our water. Water comes from the comments after Earth cooled down. So we have the word primordial. Primordial means first or early. Okay. Our atmosphere is not the first atmosphere we've had here on Earth. It is at least a secondary atmosphere, meaning that the second generation, third generation atmosphere. Okay. Our primordial atmosphere on Earth was mostly hydrogen and helium. I got a little why question there. People at home, you can answer this too. Why was our first atmosphere mostly hydrogen and helium? Oh. Okay. Did you hear that? Can I add to that? Okay. All right. Anybody else want to add to it? Why hydrogen and helium? So all of the protoplanets were hydrogen helium based because that's what the previous star was. Remember, our planet Earth comes from a previous star that blew up. And that previous star was mostly hydrogen helium. Okay? And it blew the dust everywhere. Gravity brought it over here to Earth, and Earth was mostly hydrogen and helium. However, we talked about the fact that the sun basically blew away the atmosphere because it was too hot. Okay? So the primordial atmosphere of Venus, Mercury, Earth, Mars, asteroid belt, that hydrogen and helium was lost. Okay, mainly from the sun itself. The sun was just too hot, the temperature of the early universe. The sun was very violent when it was beginning. Okay, the sun was being hit and bombarded by stuff too. Okay, just like we were being bombarded by stuff, the sun was as well. The other thing too is that Earth did not have Earth did not have a magnetic field when it was in the early stages. It did not have time to form the iron core. So early Earth did not have a magnetic field protecting it. And last but not least, Earth is not a very big planet. It doesn't have enough gravity to hold the atmosphere here. And so when the sun said too hot, the atmosphere was gone, and we were a rock planet. Okay, the only thing that survived were high melting things, like rocks and metals. Okay, and that's what Earth is. Okay, so hydrogen, helium gone, sun, gravity, all that stuff, got rid of it. So where did our atmosphere come from? Our atmosphere, the secondary atmosphere, came from outgassing, volcanic outgassing. And that's pretty much exactly what it sounds like. The volcanoes are putting out gases. And you guys know that. You guys know that whenever a volcano explodes or whatever, a lot of stuff goes into the atmosphere, including gases. However, volcanoes put out certain types of gases. They don't put out all gases. Okay? And so the early atmosphere was water, carbon dioxide, sulfur dioxide, chlorine, nitrogen, and there was no oxygen in the early Earth. There was no oxygen gas. There was water, there was carbon dioxide, but there was no free O2 oxygen gas that we breathe today. Okay. However, there was water, there was carbon dioxide, there was other stuff. So this is a time when Earth is cooled down after the atmosphere is gone. There's water on the planet. The entire planet Earth is basically covered in water. Why isn't there any continents? Why are there any mountains or anything? Why are there no land sticking above water yet? How do we make land? How do we make mountains? How do we make that stuff? Yeah, when the land are running into each other, right? Well, that takes millions and millions and millions of years. We're not there yet. That hadn't happened yet. We're still a baby Earth, right? So baby Earth is almost a perfect sphere. I mean, it's round. It's very, very round. And so water just sitting on the entire Earth when it's first forming. After millions and billions of years, the land hits and makes mountains and makes continents and all that stuff. Okay? But early Earth was very flat for the most part. Okay? Unless an asteroid hit it, unless a meteor hit it, it's very similar to like the moon and stuff. Very flat, round body. That's a good thing though. The water allows for things to start to happen. There's a lot of evidence of this happening, but again, we do not have any oxygen yet. So we have a lot of carbon dioxide, a lot of nitrogen and that stuff. So we need to fix our atmosphere basically. So early Earth did not have oxygen. Oxygen came much, much later, about 2 billion years later with a B. Took a long time to get oxygen gas. So how do we make oxygen gas? How does any planet make oxygen gas? Because oxygen is not naturally producing gas. 2 ways. I know this one sounds fancy. Photochemical dissociation. All that means sunlight breaks down water. So sunlight breaks down water, and that can make hydrogen and oxygen. Okay? So sunlight breaking down water. So if Mars wants to have oxygen, it needs water and sunlight to make oxygen. True of any planet. Okay? So planet Earth had a whole bunch of water. All the comets got together. And again, we have water because we're in that Goldilocks zone. Not too hot, not too cold. Okay? And so the sunlight breaks down the water, and hydrogen and oxygen are formed in the water first. Now, that also makes ozone, which is O3. O2 is what we breathe in. Ozone is O3. And we have ozone is a layer that protects Earth from radiation. This is a negative feedback. The sunlight is creating oxygen that is going to block the sunlight. I mean, that sounds kind of weird. The sunlight making something that's going to stop it from making more of it. So the sunlight makes oxygen. The oxygen makes a layer that stops the sunlight from coming back in. This only makes about 1 or 2% of our atmosphere, or of our oxygen. Okay. And then the rest of the oxygen comes from photosynthesis. And that is plants, or algae, bacteria. Okay. So the first oxygen on planet Earth came from bacteria, and then algae, and then your actual plants. Okay, so sunlight breaking down water for a little bit, and photosynthesis for the rest of it. That's how we got oxygen. Again, you don't need to know all the fancy equations. Sunlight breaking down water and photosynthesis. Now, again, oxygen is a resource, a very important resource. You can live about 3 minutes without oxygen, roughly. Okay. Again, we don't just make oxygen from nothing. We don't take care of this oxygen. That's all we get. That's all we got. Okay. So how do we need oxygen? Sunlight and water, and photosynthesis. That's really the only way we get it. So, are we taking care of the water for sunlight as humans? Yeah. Are we allowing algae and plants to photosynthesize very well? Yeah, keep killing them. We keep cutting them down. Okay. So again, just something to think about here. It seems like it's unlimited. The oxygen, the water. Like, oh, we got plenty of water. We got plenty of oxygen. Not really. Not really when you think about it. Okay, we're going to go a little bit faster here to wrap up the rest of our atmosphere. So we need to get more oxygen to get to today. And then we need to get rid of the carbon dioxide. Carbon dioxide, not good for us today. And so throughout the history, we got rid of carbon dioxide in a couple different ways. And they're all very unique, very interesting, very cool. Again, it sounds fancy. It's not really fancy. The first way we get carbon dioxide is through weathering of rocks. We get rid of carbon dioxide when rocks weather over time. And then those silicate materials, as they weather and combine with carbon dioxide, they produce limestone, which is a type of rock. Okay. So we have materials, we have minerals that are eroding, weathering away. And then that carbon dioxide will get turned into a rock, and it will get buried under the ground. So we took carbon from the air, buried it underground. That's going to produce limestone. That's also going to produce natural gas. Okay, natural gas. You probably have natural gas at your house or your home. Okay. So, over billions and billions of years, Earth has been taking carbon dioxide, burying it underground to make natural gas and limestone. And then what are humans doing with it? Putting it right back up. We're burning it, right? We're using natural gas to cook and make electricity and all that good stuff. We're taking millions of years of Earth's history of carbon and putting it right back into the air. In decades, not millions. Right? All right, that's only the first one. The second way to get rid of carbon, and again, we need to get rid of carbon out of our atmosphere for us to be where we are today, is photosynthesis from plants. Okay? Plant will breathe in carbon dioxide and put out oxygen. So that's how you get carbon down, oxygen up. Plant, trees, that entire mass of a tree comes from the carbon dioxide it's breathing in. It comes from a gas. It does not come from soil or water or anything like that. That huge tree weighs, 20,000 pounds, whatever it is. It's all coming from carbon dioxide. It is storing the carbon in the tree. That tree dies, falls on the ground, gets covered up, gets buried, put the carbon in the ground and out of the air. And over millions of years, that turned into coal. And what are humans doing with coal? Burning it, putting it right back into the atmosphere. Again, you're talking millions of years of burying the carbon dioxide and putting it all back into the air in a matter of decades. Okay. Yeah, not the last one. The last one, we're getting rid of carbon dioxide, is the ocean. The ocean can absorb carbon dioxide and be a sink. And it can collect the carbon dioxide. Okay? And they actually do the most. Ocean take in the most carbon dioxide for us, even today. Okay? However, that is changing the ocean water when you put more and more carbon dioxide into it. We'll learn more about that later. The other thing that can happen here is the animals in the water can use that carbon dioxide for themselves. And so the organic material, the biological material in the ocean can take in the carbon dioxide. And when the living animal dies, they fall to the bottom, they get covered up, and they get buried. The carbon goes from the air to the water to the animals underground, and it gets stored under the ground. And that organic material from the ocean turns into oil. And what are humans doing with oil? Sending it right back up. Okay? So as we get it out of the ground, as we burn it, as we use it, that carbon dioxide is going right back into the atmosphere. And again, you're talking about hundreds of millions of years of Earth's history bearing that carbon, honestly being released in 100 years, 150 years. You telling me that's not going to change things? Yeah, that's probably going to change things. Okay? So what we need to do today as humans, and we'll talk about this for the rest of the year, figure out how do we take that carbon dioxide and put it back under the ground. You know, get it out of the atmosphere. The easiest way would be to plant trees. Right? Plant. Are we doing that? We're cutting down a lot faster than we're planting. Now, don't get me wrong. Foresters, people who cut for lumber, they plant trees. Okay? They're not dumb. They want trees in the future. They plant down trees. They plant trees. They're cutting a lot harder than I can. Okay? Okay, yes, I asked him today. He told me you work Bloomberg today. I asked him. All right. So, all right. When you, well, not us, when Earth buried the carbon dioxide, increased the oxygen, it also left the nitrogen there. Nitrogen is very hard to get out of the atmosphere. Very hard. We'll talk more about that later. But it's okay. We're adapted to that. When you get rid of the carbon dioxide, you increase the oxygen, you end up with our atmosphere today. Okay? Our atmosphere today, looking at planet Earth, is about 78% nitrogen, which coming from the outgassing of volcanoes. We used to have a bunch of carbon dioxide. We got rid of it. Well, you know, not we. Earth got rid of it. And then it increased the oxygen from water and photosynthesis. And that is our current atmosphere today. Okay? A little bit of water in the atmosphere, not much compared to everything else. Mostly nitrogen. So every breath you take is mostly nitrogen. Okay? And you breathe right back out. And that's fine. Again, take a wild guess what we're doing to that carbon percentage in the last 150 years. And not like, oh, it's going up. It's going straight up. It is skyrocketing, okay, in the last 150 years. And yes, we can measure that. We'll look at that a little bit later. All right, compare that to Venus. Right? No nitrogen. No volcanic activity. Okay? No oxygen, because again, no water, no photosynthesis. Mostly all carbon dioxide. Okay? Take a look at Mars, though. Mars is interesting. Mars does have a little bit of water. Oh, okay. Mars also has a little bit of oxygen. Where did that oxygen come from? Where did our oxygen come from? Water or photosynthesis, right? So scientists think that Mars once had liquid water and possibly things to photosynthesize and make oxygen, okay? So what do we do today? We don't see the trees, we don't see algae, we don't see bacteria, we don't see water. We build a rover and send it off to Mars and go find it for us. Literally, last week. I mean, this is what we're doing. And this is why. This is why we think that happened. Because Mars does have an atmosphere, not nearly as thick as ours, but it's there. However, check out Mars' carbon dioxide levels. Not somewhere where we are going to go to Mars and start walking around Mars. Even if we terraformed Mars, even if we went there and we tried to fix the atmosphere, getting rid of that much carbon dioxide is going to be very, very problematic, considering we can't do that today here on Earth, right? So trying to take 96% carbon dioxide, increase the oxygen is going to be very difficult to do. We'd be better off just building a habitat and just living in a bubble with oxygen in it. Or going to a different planet if we could do that in the future. Yeah, that's kind of a bad picture, but yeah. The surface pressure has to do with kind of what's going on with the gravitational pull from the sun as well. All right, the last slide I have is not really that important. It kind of shows you the temperature of our atmosphere, and also kind of showing you that our atmosphere is actually very, very thin. You can climb a mountain and not escape our atmosphere, but you can get to a point where there's not very much oxygen left, okay? And you can basically kill yourself in the process of doing that. Okay, it's called the kill zone. How do you do it? Our atmosphere is not very thick. Okay, our oceans are much deeper than our atmosphere is. And of course, you guys probably know that already. You go in a space shuttle, you're out of there pretty quick, pretty fast, the atmosphere. If you're in a plane and you're flying and they lose cabin pressure for whatever reason, they drop down the oxygen mask because there's none up there. Okay, the atmosphere is not that, especially the oxygen, it's not that thick. The last thing I just want to point out in the periodic table, if you look here, oxygen is kind of heavy compared to nitrogen. So oxygen has a mass of 16, nitrogen has a mass of 14. Oxygen is heavy, it falls to the ground. So oxygen is down here. You get in a plane, no oxygen. There's still nitrogen, still other gases that are up there, okay? But oxygen is not a very, it stays low to the ground, which is good for us. It's very good for us. But as you climb, as you go higher, you get less and less oxygen. If you ever go travel anywhere, you get altitude sickness, that's what's going on. You're not getting the oxygen your body's used to. Especially if you go to like to Denver or to the mountains, things like that. Okay, guided note, I hope they're kind of finished. I hope I answered all the questions that you can there. Hopefully you learned something. I know that was not very engaging. I apologize for that. Next week, you're going to get a couple more activities. You're actually going to do some stuff next week. And, we can kind of work together on that kind of stuff next week. That's about it for me. Any questions or anything? I know I talked a lot. I normally actually don't talk very much. Not like that.